So problem number 3 from our exam number 1 is a block being pulled up an incline of angle theta above horizontal by a constant force. You can imagine a string with tension T if you want, with a constant force. And you're told to, actually I say constant force T for tension, draw a free body diagram for the block, okay, with all the forces and the coordinate system, magnitude and direction of the contact forces, acceleration of the block in terms of other parameters you're given, and G, and show that it makes sense in one of the sensible limiting cases. So to get started with this problem, we have to draw the free body diagram. So for 3A, the free body or force diagram, I have a straight edge, but you can make a sloppier drawing without a straight edge, that's fine. So we have an incline of angle theta. We have a block of mass m sitting on the incline. We're told it's pulled up with a force T that is along the incline, going up. There's contact between M and the incline, which means there's a normal contact force perpendicular to that interface. The direction of the force on M is up in this sense. And we have the weight, or mg, pointing vertically down. I have to pick my coordinate system, and I'll just choose x down along the incline and y perpendicular to it. It would be okay to reverse the direction of x or y, and or y if you want. It would not be wise to choose a horizontal and vertical axis, although you could do it and solve the problem correctly. Choosing something else arbitrary would be a poor thing to do. So in any case, the answer to A is this drawing, or at least the drawing with M, and you could draw it as a point particle if you want. That's my choice of coordinate system. Let me just point out there are 3 forces. 3 external forces. That's all we care about, is external forces acting on my system. My system is the block mass M. You've got T, the normal force, and W equals mg down. Although you don't have to spell this out, you just need the drawing. Okay, part B asks you define the magnitude and direction of any contact forces on the block. Well, we haven't gotten to friction yet officially in time for this exam. That's chapter 6. In any case, it's a frictionless incline. So the only contact force in this case is the normal force. So we need to solve for the normal force M. Okay, and how do we do that? Well, to solve for that, we can use Newton's laws and say that the sums of the forces in my x direction have to be equal to the acceleration in the x direction. That'll be part C. The sum of the forces in my y direction will have to be 0 because this mass isn't moving at all in the y direction, certainly not accelerating in the y direction. So to make progress on either of these questions, we need to express each of these forces in terms of my coordinate system. Well, n's in the plus y direction, t's in my minus x direction, but we need to convert the weight, w or mg, into components along and parallel to my directions. Let me just redraw my incline. That's my angle theta. The weight is straight down, so this is the weight pointing straight down. Okay, but I need to resolve into components along or parallel to x along the incline and perpendicular. So this will be my weight component in the x direction. This will be my weight component in the y direction. Notice this angle is theta. This angle is 90 minus theta. So this angle is theta. So I can resolve these two components by saying the x component will be the weight, or mg. Sine of theta is opposite over hypotenuse. So it'll be mg sine theta. And notice that this will be in my positive x direction. Okay, my component in my y direction will be mg. Okay, now if this angle is theta, cosine is adjacent over hypotenuse, so mg cosine theta. And notice this will actually be in the negative y direction because I said plus y is up and this is pointing down. But right now I'm just writing the magnitudes of those components. Okay, so now we can use the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. And that's going to be equal to 0. The sum of the forces in the y direction, let me just write what they are. I've got a normal force in my positive y direction from up here. I've got this component, the y component of the weight, which points in the negative y direction, so I'll write that as negative mg cosine theta. That's equal to 0, and we can immediately solve for the normal force equals mg cosine theta, and that'll be in the y hat direction. Okay, and I did ask for the magnitude and direction, so the magnitude is mg cosine theta. The direction is plus y hat for that normal force. Okay. Now that takes us to part C. Part C says solve for the acceleration of the block in terms of the quantities you're given in the acceleration of gravity. Okay, well, if I want the acceleration, I'm going to need to know the sums of the forces in the x direction. And from Newton's second law, realize that's equal to the mass times the acceleration in the x direction. And I could just start writing down all the forces in my x direction. I've got a component of gravity that's pointing down, which is my positive x direction. So that's mg sine theta from up here. And I've got a force T that was given you pulling the block up the incline, but that's my negative x direction, so that's minus T. Those have to sum for my acceleration in the x direction, but I'll stop writing the subscript x now, it's just the acceleration. And we can solve this directly for the acceleration. A is equal to g sine theta, just canceling this, dividing this m and that m, minus t over m. And that's in my x hat direction. Notice that if g sine theta is bigger than t over m, that means that you will have a positive number here, and you'll accelerate down the incline in my positive direction. And conversely, if g sine theta is less than t over m, the force T will accelerate the mass up the incline. So circle your answer. By the way, if you had picked plus x in the direction up the incline, these terms would just be reversed, t over m minus g sine theta. Okay, now part D is an effort to get you to check your answers, like I tried to emphasize in class, to show that it makes sense in a situation that you should be able to guess the answer to. So show that your expression makes sense for the special case if the tension, if the force pulling it up the incline is 0, and the incline is actually a vertical surface. Well, if you have a block M, let me just draw it. If you have a block M on a vertical surface, nothing pulling it up, you expect it to accelerate down at g. So what do we actually get from my formula? If you plug in t equals 0, I'll just rewrite it here. A equals g sine theta minus t over m x hat. So if t equals 0, this term goes away. If theta equals 90 degrees, sine theta becomes 1. And so we have A equals g x hat. Notice that when we tilt the incline like this, my coordinate system becomes y in this direction and x in this direction. Okay, and so x hat, positive x hat is down. And so I get free fall as expected. Done.